Welcome to section 9.4, and in this section we are going to be looking at transforming quadratic functions. And we've actually already done this once before, but it's been with the lines. So with lines we were looking at sort of slope and how that changes things. If we change the slope on an equation, it could become more steep or less steep. Or if we change the y-intercept, we could see where it would start on the y-axis in comparison to what it did before. So in this, we're going to be doing the same sort of thing. We're going to be seeing how parabolas get skinnier or fatter with their arms, or we already know that they can either be positive or negative. They can either like have arms going up towards the positive integers or down towards negative integers, just because of the a term being positive or negative. But then on top of that, we can also see how the y-intercept could potentially change things as well. So let's begin. Here is our first set of equations. If we look at this, we have f of x is equal to x squared. We have g of x is equal to 1/2 x squared, and we have h of x is equal to 3x squared. And we can also see these on this various graph. So here's our yellow, that's our yellow, or that yellow is our g of x, and I need to actually make this a little skinnier so it's not taking up the whole thing. So there is our h of x, here's our g of x, and I'll change that to pink, pink, and there is our h of x. So if we're looking at this, our normal f of x. Our normal f of x equation is this red one. It's right here. It's kind of this one in the middle, and it goes down to the 0, 0 point. Sorry that my line isn't actually getting there. Our g of x equation is this blue one. It's the nice fat one. And our h of x equation is this green one. So looking at this, we can actually see that the difference here between all of them is their front term. Our front term is what's causing things to be narrow or big. So one little thing that we can say is if we have a front term of greater than 1, we're going to have a narrower graph. If we have a front term and a term of less than 1, we'll have a wider graph. And so this is actually written on this next part right here. So the graph of f of x equals ax squared. So we're used to this terminology right now. We're looking at essentially f of x, or y, is equal to ax squared plus bx plus c. And in this case, we are only looking at this front part. So if ax squared is what we're looking at, if it is narrower than the graph of f of x, that means the a term is greater than 1. So if we have anything greater than 1, 2, if it's 2, if it's 3 over 2, if it's 3, if it's 4 over 2, that sort of thing. If it's greater than 1, then it will be narrower. If it is wider, that means you have a fraction up in front that is less than 1. So we need to, in this case, order our functions from narrowest to widest. And our narrowest function, if we actually were to do this, our narrowest function, it is our h of x is equal to 4x squared. That is our narrowest function. Our next narrowest function is this f of x is equal to negative 2x squared. And I know you're probably thinking, but negative 2 is way smaller than 1. Well, we need to think absolute value, and so that makes everything positive. If negative 2 is actually a positive 2, that is greater than 1. However, negative 1/3, that's definitely less than 1. So our widest one, we have g of x is equal to negative 1/3 x squared. Now actually, I have this all graphed up, and so I'm going to move us to the side so we can see the graph. Hold on for a second, just one quick second, and it'll appear right before your eye. Okay, so if we were to look at this graph, we can actually see how they are wider versus narrower. So actually narrower versus wider. We need to look at our h of x equation, and our h of x equation is this bottom one in green. And so if we were to actually find that on here, our green equation is this tiny little guy right up here. It's nice and narrow. Our next one is this f of x equation, and it's negative 2 And that equation is right here in this red. And our pink equation, this g of x, is our very last equation, and it's nice and wide. So we can see that we're right. If we have something that's less than 1, it's going to be a nice narrow, or it's going to be a big, huge, wide graph. And if it is greater than 1, it's going to get narrower and narrower and narrower, steeper and steeper. So now let's move on and actually let's see how things can be what's called vertically translated. So we've seen how they get narrower and wider, and now we're going to look at vertical translations. So we have this situation. We have f of x is equal to x squared, g of x is equal to x squared minus 4, and we have h of x is equal to x squared plus 3. Now if we look at all these things, we actually can see them graphed. Our first equation, that f of x, is this x squared, and that is simply this red one right here in the middle. That's awesome. Goes through the origin. That's pretty cool. Our next one, our g of x, is this one that's at negative 4, and it's the one that goes furthest down. It's this big blue one, and it crosses at negative 4. And our h of x is this green one right here where it crosses at a positive 3. So if we look at this, it's simply based on our final term, our constant. It tells us where we're going to be starting vertically. So let's see the write-up on this one. So the graph of a function f of x equals x squared plus c. So once again, we're looking at just simply this whole situation where we have y is equal to ax squared plus bx plus c, and this time we are actually ignoring this middle term altogether, and we're only looking, and we're actually not even paying attention to a, it's just simply a 1 in there. So we're looking at x squared plus c. So if we look at that basic situation, the graph of the function f of x is equal to x squared plus c is the graph of f of x equals x squared, translated vertically. So f of x equals x squared, that means it goes through the origin. It's a graph that goes right through the origin. It's nice and basic. That's our parent equation. And so we're relating everything back to that f of x is equal to x squared. So if c is greater than 0, if that y-intercept term is greater than 0, then it's translated that many units up on the x-axis, or y-axis. If c is less than 0, then it is translated down c units on that y-axis. So let's describe the vertical change up from the parent function. Our parent function is always this f of x is equal to x squared. So let's see how we can compare these. If we look at this g of x is equal to x squared plus 2, it is translated up vertically 2 units. Nice handwriting, it's awesome, right? Our other one, h of x is equal to x squared minus 5. This is translated, I forgot my D on this one, down vertically 5 units. So those are sort of our translations that we can see. And I can also show you a graph of this one. Hold on just one moment. You'll see it appear before your eyes. All right, so there is our, whoops, I just moved all that. There is all of our information that we just did. You can see that there is our h of x. H of x, it is translated down, and then right here, this green one is our g of x. It's translated up 2 units. It should be 2 units, it's 3. I messed up on that graph. It should go down to here and be up like that. So there are our equations there. Now we're going to try one last sort of ultimate test of our new skills that we're learning, the ultimate practice with translation of quadratics. I want you to compare the graph of each function with the parent function, f of x is equal to x squared. So if you look at this, how does this graph g of x is equal to negative 1/3 x squared plus 2 change with the f of x? First of all, we can look at how is it narrow or widthwise. It's less than 1. The absolute value of the a is equal to the absolute value of negative 1/3, which equals 1/3. That is less than 1. So because of that, it is I almost screwed up there. I almost said narrower, but it's actually wider. It is wider than that parent function. And then we can also see from this 2 right here, and it's a positive 2, it's translated up 2 units. So that is that answer. Let's see if we're right. Let's pull up a picture really quick. Actually, if we look at this picture right here that I just added in, I forgot one thing. We need to also pay attention to the fact that it was negative in the first place, that A was negative. So it is also pointed down. Pointed down. It is wider and it is translated up 2 units. So there's this blue line is our g of x, this red line is our f of x. So if we look at that, it is wider than its original. It's also upside down compared to the original, and it's translated up 2 units. So now let's look at this g of x here, and it looks like this one's a little simpler because there's no negative, which is nice. So we see a 2, so that 2 is greater than 1, so that means it is narrower, and it is translated down 3 units. And we can see that right here in this -3. So it's translated down 3 units. Hold your horses just one sec and let's check our work with a quick little graph. So here's our graph of this situation. Here is our g of x, and this red one right there is our f of x. So we can see exactly what's happening. Our g of x is narrower. We can certainly see that it's narrower even up here at the top. And then it is also translated down 3 units. So I hope this helps with your homework. Enjoy, have fun. I really enjoy this section. It should be a really good time, and it shouldn't take a lot of time. If you have any questions, as always, please text, email, or call me. Thank you.